Ladies and gentlemen, it's my pleasure to introduce today's seminar. The speaker is well known to all of us. He's Zhidenko, and today's topic is about even horizon geometry for this overtone quasinormal also. Please.
Thank you. This time I would like to talk about our more recent works, and to be honest, I hope that more of them will be published, but well. I would like to talk about overtones in the quasinormal spectrum, so I will start from the very beginning, from the ring down. Then I will briefly explain how this is described by solving of basically linear differential equations. Then I will introduce the so-called spectral instability, that is to say about if we do tiny geometry modifications, how this will change our spectrum. And then I will actually talk about our works, about the fact how these overtones can be used for probing the near horizon geometry, and because of the uniqueness theorem in general relativity, this means that we can actually test our theory of gravity to see if we have any deviations from the general relativity in the regime of strong field. And also I will briefly talk about other phenomena that we can encounter when we consider alternative theories, which is called echoes, and I will compare these two methods, let's say, how they can be used for this kind of tests. And finally, if I have time, I will introduce also a general representation for the black holes, which actually look like Schwarzschild black holes, like what we currently do observe, but can differ a lot near the horizon, and that's why this is the framework for testing of the alternative theories of gravity. So I would like to start from this scheme of what was observed by the LIGO-Virgo collaboration yet in 2015. In 2016 it was published. The collision, the gravitational wave signal from the collision of two black holes. And if we look at the profile of gravitational wave which we observe, we see that actually we can see here the three stages of this signal. At the first stage, when we have in spiral phase, the signal from in spiral phase is basically the frequency oscillating signal with the frequency twice bigger than the frequency of rotation of the black holes. Then we have a merger phase of two black holes. And as a result of this phase is the one black hole resulting black hole, which the only black hole which we have at the final stage, and that's why we have no any source of the gravitational wave signal. What we have is the ring down, is the gravitational wave, which is just the rest of the perturbations. They are propagated to us, and because this signal is absorbed by black hole and scattered to the infinity, we have exponential decay of the signal here. So we have these oscillations which decay exponentially. And this kind of oscillation is very convenient to describe by complex frequency, where the real part is the actual frequency and imaginary part is the decay rate of the oscillation. And because the fact that we have just a black hole, and in the background of the black hole we have a gravitational wave that, and we can basically neglect the high order contributions, we can use here the linear approach very well, because well, black hole is much bigger object compared to the gravitational waves. So the general approach is just to consider the small perturbation, the gravitational waves are our small perturbations to the background metric, which is just a black hole, yes? And after some algebra, the Einstein equations can be reduced to the wave-like equations. In the simplest case, when we have spherical symmetry, after separation of variables, we have this kind of wave-like equation. And a solution of this equation is what is describes our ring down phase. And we can represent it as a superposition of the complex frequencies, decaying oscillations. And these frequencies satisfy the eigenvalue problem of the linear equation, differential equation 1, yes? So, and actually this means that we have not only one decaying oscillation, but a superposition of infinite number of decaying oscillations. And of course, from the practical viewpoint, we have the frequency which has the smallest absolute value of imaginary part, which decays slower than others. And this is actually what we see here in the ring down phase. But in fact, we see here that actually, in addition, we have, strictly speaking, infinitely many other decaying oscillations. And our hope is if we get the signal from the black hole, gravitational wave from the black hole with a very good relation between amplitude and noise. Yes, if we get small noise in the signal, we can detect actually not only the dominant frequency, the one which decays slower, but also maybe a few of subdominant, which we call overtones. And what is interesting about this is that if you look at the black hole, at the effective potential related with the particular black hole, then we see that the dominant frequency it depends mostly on the behavior of the potential peak, of the behavior of the effective potential near its maximum, which basically this behavior is described by the black hole parameters such as mass, and if in more general case, let's say rotation parameter, but in spherical symmetry, this is just a black hole mass. Yes. This can be understood also if we look at the inverse problem. We can make some kind of transformation of the wave-like equation and consider instead of the potential V, the potential with negative sign. So this peak becomes gap. And then our quasi-normal boundary conditions are translated to the bound state conditions. So we have this correspondence between bound states of the inverted potential and the quasi-normal modes in this background with the potential peak. And then it is easy to see that this ground state of the bound state, the bound state with the lowest energy, it depends on the behavior of the deepest part of the gap. So we see if we change a little bit our effective potential due to some maybe other objects or perhaps new physics, we see that our dominant frequency does not change much. If we compare the time domain profile, this is already in the logarithmic scale in order to see this picture better. Yes. So we see that if we change a little bit our effective potential, the profile does not change much. We see that the dominant frequency is basically the same. It's slightly different, but of course we always have some accuracy of our observations, right? So from the point of view of this dominant oscillation, we don't see much difference if we have something, some corrections to the potential. But if we subtract this dominant oscillation, this damped exponent, we see that starting from the next frequency, we see that the profile is completely different. So if we have signal sufficiently good to do this, to extract the dominant frequency and look at the subdominant, at the overtones, we see that the picture is completely different. And potentially, we can think that we can use this data to probe our geometry, let's say here. Yeah. And the first question is this different picture due to our small change, or is it just a random profile which we get whatever small correction we add to the geometry? And of course, we cannot get rid of the small corrections to the geometry because we and everything, let's say our Earth, everything is just a small correction to the black hole geometry. We don't have single black hole and nothing else in the universe. And in this view, the problem of spectral instability is considered. I would like to advertise this paper and references there for more details of mathematical formulation of this problem. And the idea is very simple. If we add something to our effective potential, we look at the spectrum, how the spectrum, how our complex frequencies are changed. And if we have bounded absolute value of the difference, then we can say that our spectrum is stable, and if we take sufficiently small change of the geometry, our spectrum changes just a little bit. And this indeed happens if we have self-adjoint differential operator, but unfortunately, in the case of quasi-normal problems, it's not the case. We cannot guarantee that this coefficient is finite. So, in principle, if we do formulate our problem in general rigorous mathematical way, we see that the problem leads to the instability of the spectrum, That is to say that we can find small corrections to the effective potential, which just breaks down the picture. We have completely different spectrum. This was shown in this paper here. Yes, for the ad hoc kind of correction to the effective potential, and we see that for this small amplitude of the correction, blue dots are the new modes, the pseudospectrum, which we have instead of the red dots, which correspond to the Schwarzschild black hole spectrum. And in addition, they observed even additional modes like these squares, blue squares here. So if we consider just arbitrary correction to the effective potential, we see completely different spectrum. So at the first glance, our overtones are just random values. We cannot extract any information from there. But if we limit ourselves by physically relevant changes to the effective potential, that is to say, we consider some small localized correction to the geometry due to, let's say, some external bodies, stars around the black hole, or accreting matter, etc. And in this paper, there was done extensive work on this topic, and they found that actually the dominant mode, at least, it is stable. If we change slightly the effective potential at some distance from the black hole, the dominant mode remains approximately the same. So we should not worry about the external matter when we detecting the dominant frequency of the gravitational wave signal. But the question about overtones was still open. And what we did, we considered the high overtones in this case, in the case of effective potential plus some augmentation due to some external matter. And we chose the form of this bump, of this augmentation, such that it does not affect the horizon and infinity. Yes?
Little comment, short, if you will. Just maybe should be explained that pseudospectrum does not mean that it's not spectrum. It's spectrum of deformed black hole. Yes, so it's also the same quasi-normal spectrum.
Well, it's quasi-normal spectrum, but it's for this kind
for this kind of deformed
non-physical, let's say, in this case, non-physical correction to the geometry. Okay, so we have considered this kind of augmentation, and we see that actually all the dominant frequencies, not only the dominant frequency, but also the first overtones, which have the smallest imaginary part, which can be potentially detected in the signal, they don't change a lot if we consider such kind of correction to the geometry. So from the Schwarzschild black hole, for instance, even if we have something around it, we detect the overtones, we will get not random values. We will get something meaningful, something that describes, that corresponds to the geometry of our Schwarzschild black hole. So this means that the significant change of the values of overtone from the physical point of view may come only from one source, from the corrections near the horizon of the black hole. Or, in other words, if we have not a Schwarzschild black hole, but some black hole which is a solution of some alternative theory, let's say due to quantum corrections or scenarios with extra dimensions, etc. Because in general relativity we have uniqueness theorem, and if our general relativity is valid everywhere, if we have indeed Schwarzschild black hole, then not only the dominant frequency, dominant quasi-normal mode, should be the one which is predicted by the Schwarzschild spectrum, but also all the overtones must be Schwarzschild overtones. And if we see some difference in the spectrum, then it might be a signal of the new physics, of some kind of corrections to the gravitational wave theory in the regime of strong field, because near the horizon we don't have much experiments yet, so we can assume that there are some kind of corrections there. And in order to test this hypothesis, we use the general framework for describing the arbitrary spherical symmetric black hole, not just Schwarzschild. Schwarzschild is the particular case. So we use agnostic approach here for the behavior of the geometry near the horizon. And we consider the metric, which basically in spherical symmetry is defined by these two functions, a and b. Yes. And these functions a and b, when we have just a and b equal 1, we have Schwarzschild geometry. Okay? And also in these two functions, we have certain coefficients which measure our deviation from the Schwarzschild solution. This parameter epsilon is just a relation between mass and the event horizon radius. Yes, for Schwarzschild it is 0 because radius equals to m. Coefficients a0 and b0, they are related to the post-Newtonian parameters of arbitrary theory, and our current experiments in the solar system give this bound, so we can safely neglect these two parameters. We can think that for now that a0 and b0 are 0. And we also have infinite number of parameters a1, a2, a3, b1, b2, b3, which describe these two functions near the horizon. That is to say, these parameters, they introduce arbitrary deformations of the metric near the horizon. And the way how they introduce through the continued fraction allows us to establish hierarchy between these parameters and say that actually from the practical purpose, the most important are, let's say, a few first of these coefficients. And of course, if we want to describe our geometry more and more precisely, we can add more and more corrections to this continued fraction. But in order to get the dominant effect, we can limit our consideration by, let's say, first few of these coefficients. And this allows us to construct the geometry which is practically indistinguishable from Schwarzschild at large distance, but at the horizon the behavior is completely different. And for example, for this set of parameters, yes, we see that indeed this is what happens. The dominant frequency, which is associated with the potential peak, remains basically the same place, but all other frequencies differ a lot. Starting from the from the second overtone, we see that the difference is already like several tenths of percent. And I don't show here the effective potentials because by naked eye it's not possible to distinguish these two potentials, the Schwarzschild potential and this one with these parameters, because the only change which introduce this parameter is the behavior just near horizon. Particularly, we have Hawking temperature which is 50% higher than Schwarzschild. But if you look at the effective potential, it looks the same. Yes, the correction is very small. At the same time, we have completely distinct spectrum of the quasi-normal modes, and we can hope that if we see this kind of divergence from the Schwarzschild, or let's say Kerr black hole, in the spectrum of the gravitational wave detected by future beta antennas, which provide better signal-to-noise ratio, we can extract some information, and for instance, we can find some kind of estimations for these parameters of deviations from Schwarzschild. Another feature which we have in this case when we modify geometry of a black hole near the horizon is that we can observe also what is called echo. Echoes we also have in the, let's say, in the ring down signal, but the point is that the source in this case is that our signal goes to the horizon, and because of the deviation from Schwarzschild, we can have some kind of reflection from there. And then this reflection is scattered around our main peak. So after main ring down signal, we can have, in principle, secondary signals, which are called echoes. But the point is that echoes are quite, first of all, they appear at later time, yes? So we don't really know if it's signal indeed from the horizon, or, for example, from some other source, yes? And also, these echoes should have very small amplitude because it's secondary scattering. On the contrary, if we detect overtones, we don't have these problems. Overtones we can detect at the very beginning of our signal in the ring down phase, because that's the moment when they are actually important, because they decay much faster than dominant mode. So if we detect it since the beginning. So the amplitude is significant comparing to the echoes. And also, because we know that they are stable against modifications of the geometry at the distance from the black hole, these quantities, they actually depend only on the black hole geometry near the horizon. So from the physical point of view, of course, if we are talking about mathematical formulation, it doesn't matter where the corrections, where the geometry modifications are placed. But physically, we know that we cannot have different asymptotical behavior of our metric, and we cannot have something big near the black hole, because otherwise it's not already a problem of a single black hole emitting gravitational wave. We have some, in this case, we have some more complex problem. Yes, but if we have one black hole emitting a gravitational wave signal, then corrections to the overtones come only from the near horizon, from the near horizon geometries, and we can actually we hope that we can test in this way deviations from the Schwarzschild geometry, that is to say, from the general relativity. And the final step, which I would like to present here, is our proposition for the generic description of such a Schwarzschild black hole mimicker, which is a black hole that has geometry similar to Schwarzschild everywhere except to some region near the event horizon. And in order to construct this black hole, we just neglect higher order parameters, A3, B3, etc. Yes, so we have only these 5 parameters: epsilon, A1, A2, B1, and B2. And 2 of these parameters, A1 and B1, we can fix by requiring that the shadow radius and Lyapunov exponent for the circular orbit are the same as Schwarzschild. In this case, we are left with only 3 parameters, and this epsilon, which is relation between radius and mass, should be small. So the significant parameters are only 2, A2 and B2. Well, and to illustrate how this works, I would like to show that, in addition, we have the same effect on the dominant quasi-normal frequencies, because when we have a large multiple number, we have this approximated formula, which basically says that if we fix radius of the shadow and Lyapunov exponent, we also have the resulting dominant mode, dominant quasi-normal frequency, close to the Schwarzschild frequency. And at the same time, we can have quite different value for the Hawking temperature, which is a characteristic of the horizon. For the practical purpose, actually, it is possible just to use this approximate formula for small epsilon. Yes, so we have even an analytical representation for our framework for the Schwarzschild mimickers. And if we compare, for example, some observable quantities for such black holes, we see that, for instance, innermost stable circular orbit frequency varies within 1% if we change these parameters, parameter A2, for example. Yes. At the same time, the Hawking temperature changes quite a lot, and the same is applied to the higher overtones. So we can use actually this approximated geometry for the black hole mimickers to study some phenomena which depend on the near horizon geometry. And if we are able to detect some signal of those phenomena, then we can test the geometry, or let's say find estimation for these parameters of deviation from the Schwarzschild and compare them to what is predicted by alternative theories. Unfortunately, for the gravitational wave signal, of course, it is hard to do having only the geometry, because if we have alternative theory of gravity, then we must consider correct perturbation equation. We must derive the equations for the gravitational waves from using the particular theory. But if we study some phenomena in the background of given black hole, then we have this geometry which can be used as a framework for such to describe such phenomena. That's all what I wanted to say. If you have any questions, thank you.